I welcome you all to the second class of doping. In the last class, I have discussed about the two processes of doping. First one is the diffusion, and the second one is ion implantation. Today, I am going to elaborate the second topic, ion implantation. Now, what we do for doping using ion implantation technique is essentially a a simple ion bombardment process where you use the ion beam and these ions of the materials that you want to dope. So you prepare ion of this material and accelerate them with some energy, which is done in using ion accelerator, and then you bombard on the surface of a substrate. When you bombard, depending on the energy of these ions, they penetrate into the material and they get doped there. So of course, after the bombardment, all you need to do is to anneal the samples at high temperature such that these randomly deposited atoms into the material can find some of this lattice site and acts as a dopant. Now this is depends on the energy of the ions and of course the atomic number and the mass. So these are the two important things, important parameters that you need to choose very selectively. And this class I'll try to explain you that what are the guidelines of selecting the energy and the materials for a particular doping of a material. Now, there are several ion accelerator available in our country. So this one is the figure of IUAC in New Delhi. So 15 MV accelerator is there. So you can see this, but the accelerator is installed. It's vertically. It's very huge accelerator. And there is another one at Institute of Physics, Bhubaneswar. So you see this tube actually where you accelerate the ions. So you have this side somewhere, you have ion source, you accelerate them, and this through this pipe the ions comes, and then this ion beam actually enter into different beam line. As you can see here, you have several such beam line for different purpose, and one of this beam line I think is used for ion implantation, and other beam lines are used for different other purpose, nuclear physics experiment, and then surface interface characterizations like Rutherford packs spectrometry, etc. There are many more other than these two in the country. So there are facilities available in our country as well for ion implantation. Now, what you see here is basically the beamline outlay layouts of Institute of Physics ion beam accelerator, where you have the source where you do basically you get ions, you prepare ions. So this is essentially a it's called MC sneak source where any element can be ionized in this case, or you can also have alpha source, alpha ions, and then you have initial part where you accelerate it, and then this is the major final accelerator part where you actually accelerate the ions, and using analyzing magnets you basically control the deflection, and they enter into different beamline by the switching magnet. So at different degree, this different angle, these beamlines are situated, and you can use them for different purpose. Now I will in this case the 0 degree is the ion implantation beamline, uh, in IUP, Institute of Physics. And you have another 45-degree beamline where you can do other like other pore back scattering spectrometry experiments. You have micro beamline also. So surface beamline. So all sort of experiments can be done. Now again, so this is the main reference which I already mentioned in the last class. So so this is more on summarizing the important aspects of ion beam implantation. But if you are those who are very serious to learn a little more in depth, so then there is another reference book which is ion implantations and synthesis of materials. So you can also have a look at that. Fine. So let's start the topic. Basic understanding of ion solid interaction, because that's the important topic to understand even in the ion implantation power doping. So when you use ion beams and it interacts with solids, there are a lot of things happens which I am going to explain you. Now what you do is, as I said, that inside the material you have single crystal substrate. Atoms are periodically arranged, and these are the ions which you bombard on the surface, and after the bombardment they penetrate into it. Now what you should notice is that when these ions enter into the crystal, they actually damage the structure, right? Because they occupy some of the space, so they damage the structure, and there is sort of like kind of random uh, depositions of the atoms inside the material, right? So this is so you implant the ion, and then all you need to do, if you anneal it, then these atoms, I mean all atoms started diffusing uh, inside the material, and they can actually settle in structures where these atoms can sit in a specific lattice site, and that can be considered as a dopant atom for, for this material. Now, in case of diffusion process, I discussed that. In, just to remind you that what you do is that you use dopant gas, and then you deposit a thin film, right? And then using a mask, silicon dioxide mask, and then this part you cover, you seal this part, and then annealed at high temperature, around 1000 degrees centigrade, and then these atoms, the thin films that you deposited, they diffuse, and a region will be doped. So that is the process that we discuss. Now what happens to the ion beam? Now it's almost similar thing, but you don't deposit the thin films there. What you do, again, you use mask, and so you open up a small region where you want to dope, and then you take phosphorus ion beam and you bombard it. Now remember, since this SiO2 layer is acting like a mask, so this part will not be deposited. Some of the ions will be entering here, silicon dioxide layer, but which you can remove later. Only this exposed part, so you deposit, you basically deposit some of the ions, phosphorus ion, in this region, and as a result, after the processing of the samples, we can make this plus as n-type silicon. So this is p-type material, this is n-type material. So this is how you can do doping using ion bombardment. What are the advantages of these two processes? The first one is using dopant gas, and second one is dopant ions, so using ion beam. Now there are a few advantages, but both the techniques are of course used. Now advantage of ion implantation, this one is relatively contamination free. Now remember that when you grow thin films, it's grown on under vacuum, right, or inside a chamber with inert gas environment. So there is a chance that these thin films, when you deposit, contains some contamination, and when you anneal them, so this contaminant also will be diffused inside the material, so you may not have a purity in the doped region. But in this case also, when you do ion bombardment, it is also done under vacuum. But the gas molecules that you have inside the chamber may not be bombarded inside the material, because the bombardment depends on the energy of that, and this gas molecule do not have that energy to penetrate. Now, so relatively contamination free, and this one is low temperature processing. Low temperature processing in the sense that here you need to annihilate at really high temperature, but here, since that just by using a particular energy of the ions, so these atoms can go very deep into it. Little bit temperature, annealing temperature can settle the atom inside the material. So that's one of the important advantage. Second is high control outwards. So that's something like up to 10 to the power 12 to 10 to the power 18 in dopant per centimeter square, which you can control very efficiently using ion bombardment, because all you do is that you measure the current of the ion beams that is coming, and from there you can calculate the flux and how many ions you have bombarded in the material. That can be calculated very precisely. However, in this case, the thin films that you deposit is sort of like with a certain thickness, and apparently, diffuse. It may not happen that all the atoms are diffuse. So some sort of errors will be there in the those calculations as well. So that is one of the advantages of ion implantation. Good control of implant depth. So what is the depth of the substrate that you want to deposit? So that's again by selecting the ion energy. So depending on the energy, it's certain up to certain depth. So that can be controlled just by controlling the energy and the choice of masking. But in this case, normally SiO2 are used, but here you can use SiO2, but many other materials also just use the mask. Shadow mask also can be used to control the area where you want to deposit. Okay, so there are many more, but these are important advantages of ion implantation. Now, as I said that ion solid interaction is very important process that takes place when you bombard a material substrate with ion beams, and there are a lot of things happens inside that. Essentially, if you look at one of these atoms inside the surface, so this is also ions, and it actually interact with the nucleus of the atoms, and also the electron clouds that it has. So there are two different kind of interaction that happens. One is the interaction of the ions with nucleus, so, and it is essentially treated as a nuclear collision. So it's like two particles colliding each other. Out of that, one particle is ions with high energy, and of course, since this is a charged ion, so it also interacts with the electrons. Okay, so you will be dealing with two different kind of interactions. One is interaction with nucleus, which is essentially is classically treated in this case as a nuclear collision, and of course the interaction of ions with the electrons. So there are two different kind of process, and these two processes leads to deformation in the crystals, so which is another important process that takes place, and one need to understand that how much damage this ion bombardment using ion bombardment you made. Now, as I said that just classical treatment of collision of two particles, so of the binary collisions that we already learned in your classical mechanics course. So what you have here is, so you have a target particle, and this target particle is atom, right, inside the substrate, right? And you have another particle which is ions with mass m and energy not primed. So that's it's coming with not primed energy. So now it have the collision, and after the collision, so it some of the energy of the incident ions is transferred to the target particle and move in a particular direction, so making angle phi, and the particle itself, incident particle, also move deflect to in another direction, it make theta angle. So so this is a process, two body collision process. Now if you consider this collision is elastic, so that means your energy and momentum are conserved before and after the collision, and very simple calculations, you can calculate the energy of the recoiled atoms and the deflected ions, right? Deflected, yes. So you can calculate this E1 primed, that's the energy of the deflected ions with mass m1, and you can also calculate the energy transfer to the atoms because of this collision. Okay, so I'm not going deep into these calculations, but you can have a look at any of the standard book which discuss about collision of the two particles, and you can see how this thing can be calculated. Now what is important here is it's essentially kappa and lambda, so that's these are called kinematic factor, and it's essentially a factor uh, which uh, which actually is basically take a fraction of the incident energy to the ions, deflected ions, and another factor of the incident energy transfer into the atoms, right? So these are the two parts which the total, that's why kappa plus lambda is equal to 1. So this is how actually you can quantify the energy of this particle. Now remember that this deflection angle can be anything depending on the energy and the you know um, scattering cross section. So this can be deflected in any direction. This theta can even be like a 180 degrees. So it's actually uh, you know uh, reflecting back. So that's called the backscatter ion. So that is also possible, and we normally use this backscatter ion to characterize the materials, and Rutherford backscattering spectrometry is based on the ions that you which are actually getting backscattered by this atom, and in that case, of course, the mass of this ions are very light, so normally helium is used. Now the second important parameters second important parameter is called energy loss rate, which is DETX. uh, I mean due to the bombardment of ions, when ions penetrate inside the material, it start losing its energy because the energy is given to the lattice atoms, right? And at some point, it starts colliding with the atoms, and some point the ions get deposited into lost at that point lost its all energy, right? So we need to know that what is the energy loss rate, which is essentially dE into dx. The x is essentially depth, it's the penetration depth. Excuse me. Now, as I said, that there are two different processes that takes place. One is the collision of the ions with the atoms. So there's basically interaction of ions and nucleus, and other is with the electrons, right? So the energy loss is also driven by these two mechanisms. One is the nuclear collision, so energy is transmitted as translatory motions to a target atom, and the second one is the electronic collisions. So the particle excites or ejects atomic electrons because of its energy. So the both the way it loses its energy, and so there will be total energy loss should be two part. Should have two part. One is the electronic energy loss, and other is the nuclear energy loss. This electronic energy loss is E, and nuclear energy or Sn. So these are called the stopping power, and this of course depends on the materials and the energy of the ions, and the mass of the ions as well, which is a very important factor, of course. Now, so what is the impact of ion bombardment? Because when ion penetrates inside the material, it's transfer its energy, and impact is a lot, is very serious, because all it does is that when it transfers energy, it make a lot of damage. Now, if you look at the plot of this dEtx, right, with energy, so what you see that you have a nuclear energy loss, which is basically is represented by this graph, and the electronic energy loss is essentially linearly increasing, right, two component. So interesting thing is that for the nuclear energy loss is essentially happens the E1, so where you have the maximum energy loss because of the collision with the nucleus is somewhat at the lower energy side, and then it decreases as you increase the energy of the ions, and when you increase the energy of the ions, your electronic energy loss increases. Now there is a crossover which is called E2, where the both electronic and nuclear energy loss is same. Now you need to know, because the damage of the crystal is happens due to both the things, right? Now what kind of damage you need selectively, which is better for your doping process. You need to find out energy of the particles, and that will give you some kind of estimation that what kind of energy loss will be dominated there, the nuclear energy loss or the electronic energy loss, right? So now look at some of the ions, like you can have the light ions like hydrogen, barium. So in this case, when you have the light ions, the mass is low. In that case, the electronic stopping dominates for light ions. And for heavier ions, like arsenic, you have nuclear stopping dominate. So it's sort of like, you can compare, like you have a big a slab of mud, and you are basically shooting a bullet. And the bullet mass is low, but its energy is also high, so bullet can penetrate through the mud. But if you take a big piece of stone and throw on the mud, then of course uh, the stone doesn't penetrate to depth, but it makes a lot of damage on the material up to certain depth. Whereas the bullet can actually penetrate, the damage is also less. So same thing happens when you bombard ions. So the electronic energy loss, depending on the energy, of course, your damage is lower than the nuclear energy, energy loss. Okay. Now, given a couple of numbers, for example, boron implantations on silicon, phosphorus on silicon, and arsenic on silicon. Now, look at this E1 is the peak of nuclear energy loss, and E2 is the crossover. Now, when your particle mass is low, essentially lower ions, you see that the nuclear energy loss essentially dominates, and the become maximum somewhere around 3 kV, is very low. Whereas E2 is the crossover, also relatively lower. But look at the arsenic, which is much heavier than boron and phosphorus. You see that E1 is the nuclear energy loss, which is 73 kV, and E2 is like enormously high, like 800 kV. So it's important, of course, that the selection of energy of the ions when you dope a particular atom into the semiconductor material. Projected range and struggling. Now the struggling, as I said, struggling is another important parameter in ion implantation. Now what happens in this case, that you have the ions which you bombarded on the target surface, and it penetrate, and then it can counter several collision. It travel and collide with another, and finally it travel a depth, right, and get settled somewhere. So at this point ion stops, and that's the depth of penetration, and that's essentially called the projected range. So projected range can be from here to here. Now if you increase the energy of these ions, then of course it can travel longer distance. So now the depth can be controlled just by selection of the energy of these ions, right? So if you have lower energy, then of course it settles somewhere in a lower depth, and high energy it can go. Now one things also you remember, that all the ions, it doesn't mean that all the ions will be settled at that depth, because it, the number of collision encounter while it's traveling through the material may be different for different ion. So you essentially have a distribution of ions in this region, right? And in that distribution, if you look at that, mostly at this point it's not like a single line, but it's an area, or it's basically a depth where the ions, majority of the ions are deposited. So that we call the struggling, and that's essentially a depth of delta Rp. Now these two things are important, so projected range and delta Rp. So you'll have essentially a depth here, and that is called the struggling. So sorry, this one is essentially your STRA. Sorry for this typo. Now as I said, some sort of distribution. So in this case, depending on the mass, so this is the mass of the ion, this is the mass of the materials, substrate material. So you see your Rp, position of the Rp could be different, but the distribution also depends on the mass. For example, if your mass of the ion is less, then essentially you have this Rp is quite width is higher, whereas if your mass is low, uh, the mass of the ion is higher, then of course it will be much more, the struggling is very narrow. So these are all the process that you need to know, because ultimately the distribution of atoms, distribution of ions, dopant ions inside the material is important to know. Now what I show here is again the trajectory of the ion that passes through the material. Now if you have a light ions, which is the example of bullet that I had given, that when you have light ions, it can actually penetrate a high depth, right? And while it's going through, so these are essentially the uh, deflection of the ions, right? It takes place. So you see that the damage, so this really represents the damage. So the damage is less, and the ions at this point, but the damage at this point at the end will be because all the energy of the ions will be basically transferred here, and you have more damage at this one than this depth. However, if you have heavier ion, as I was giving an example of a stone thrown on a mud, so you have a lot of damage, but depth Rp is essentially low. But in this case, of course, this one is thinner, damaged region is thinner, but this can be really thick. Okay. So electronic stopping, as I said, its mode dominates for the ions of light mass and the higher energy, and nuclear stopping heavier ions with lower energy. And that is also in the earlier examples, so hydrogen, boron, so there is essentially the electronic stopping dominates, but for case of arsenic, It's essentially the nuclear starting. Fine. This again the uh, damage or the disorder of the solids that takes place because of ion bombardment. Now, yes, so there is another thing is the dose. Dose is how many ions per unit area you are bombarding. Now, if your dose is low, for example, if one ion passes, so you make damage this. But if you increase the dose, then of course you can uniformly damage and you can implant the ions, right? So if you increase the dose, but when you increase the dose, the you modify the crystal structure because you damage the material, right? So essentially this ion bombarded area will be almost like amorphous if you go at higher dose, right? So that also one has to remember that you make the area into amorphous, and you have again you have to get the crystallinity of that amorphous region back, and just by further processing. Now this one I showed another important point of ion bombardment. When we look at this is simulated, so you can do the simulation. What is done in this case is the trajectory. So these lines are essentially trajectory of the ions. To see is you bombarded 100 uh, ions uh, and penetrating depth something like half a micron thick silicon. So there are two ions is used. So one is for phosphorus, another is boron. So this is for phosphorus, this is for boron. Now what you see is the depth, the similar kind of distribution, right, trajectory distributions of the ion for both the cases, right, for two different atoms. So one is phosphorus, other is boron, right? So you can make n type and p type, right? So using that, so what you see here is that energy of these ions you need to select. So you can see first simulate it, and then you can see what would be the energy of the ions that you need to select for a specific element of ions. For phosphorus it is 200 kV, whereas for boron it is 100 kV, so half of it, but you get a similar kind of distribution of the ions, right? So that's also very important that different ions if you select, you first need to know so uh, that what is the depth of penetration and how much energy you should select. That can be simply use some simulation software, which is standard software available, which is called SRIM, and can be used as to understand to select the energy and the damage. Yeah, so schematic of atomic I mean to see what kind of damage that you get. So if you have a crystalline solid, right, so you have a periodic arrangement of the atoms, and after ion bombardment, when you make this crystallinity into amorphous, then you see you basically damaged completely the periodic arrangement of the atoms that you had in the crystalline side. So you still have some some sort of arrangement, but there is no periodicity in this distribution, so you lost the crystal structures, and this we call as amorphous. So all you need to do is to annihilate at some temperature, then of course these atoms get settled to in the similar structures again. Now there is another important aspect of ion bombardment, that you basically take a substrate and you bombard the ions in a particular angle. Now what happens when your substrate is aligned to a particular crystallographic planes, right? So in this case you bombard, and also let's say you make a thin film where you have a film of a polycrystallinity. So these are small crystals, right, but they are arranged in different crystallographic direction. Now in both the cases, if you do the ion bombardment, so there will be different effect, right? And because in this case, let's say you are shooting the ions perpendicular to this, so you see there is no atom here, so this is atomic plane, so it can actually passes through the, so the damage will be lower in this case because it get a channel through passes through. But in this case, the damage will be more because it hits at the collision. So essentially your scattering cross section increases in case of polycrystallines, or you bombard the crystal not aligned to a particular crystallographic plane. Okay, but when you align it, then of course the cross section, scattering cross section decreases, and you have different uh, kind of energy transfer and with less damage. Okay, so that is also another important. So then just to exploit that, this another technique is called the channeling, and the channeling also is used to study the material, but you need to be careful when you use ion implantation for doping, because if you implant at the channel conditions, then of course your distribution of the atoms will be different than in a random condition. Now in this case, channeling means the ions, when it's penetrate, if you align these crystals to a crystallographic plane, then there should be some kind of channeling effect that takes place. Now what do you mean by the channeling? So for example, if you look at the silicon structure, crystallographic structure, which is basically the diamond structure, and you look at these crystals at different angle. For example, if you look at the crystal from along the 100 direction, then you look like that. So you see that there are some holes which are clearly visible. So one hole here, another hole here. So if you bombard ions in these directions, you have collision by these atoms. But if your ions is falling here, then of course you'll get a channel, so it will passes through, so your collision will be less. So this is called the channeling. Similarly, if you look at 110 direction, then of course you have different kind of structure. So the point here is that if you do the ion bombardment on the same silicon substrate, one case it's 100 direction, in other case it is 110 direction, in the third case it's a random direction. So you understand that the distribution of the atoms after the ion bombardment for all three cases will be different. So that is also another important point to note down, that which way your substrate or the silicon wafer where you are selectively want to do, which way the substrate is aligned. So is the basically the crystallographic orientation of the surface. So in that way, if you do not want the channeling, then of course you have to bombard the iron not in the perpendicular direction to that particular plane, but in some angle such that you avoid channeling. Now implantation under channeling condition, as I said, that if you have the ion beam and it is channeled, the aligned with the crystallographic plane, so your ions can actually really penetrate. Now what is important here? So those ions which are directly hitting the surface atoms, they will scatter back, so you get the back scatter. And then let's say I have a element which is sitting at the interstitial position somewhere between the two planes, then of course this ions, when is passing through the channel, then of course it will collide with this and you get some kind of scatter ions. Now if you have sitting somewhere here, right, then you have different kind of scattering of that. Now what is important in this case is that you can exploit this channeling to understand the material. Let's say I have already doped, implanted some of the ions. Now if you do the channeling measurement, you will be able to understand where these implanted atoms are sitting. Is the implanted atom sitting in the interstitial position or in the lattice positions? Just by looking at the backscatter ions. Now in that case, of course, you use very low Z ions, for example, like helium ions, which can actually, which is lower mass, which can really penetrate, and the interaction is relatively lower. So you get the backscatter signal. So you keep your detector which can count the backscatter photon, backscatter ions, and then you see how the backscatter ion number of ions that you collect changing with energy. Right? So so the ions which will be scattering back from the surface atom will have higher energy, but which ion will be getting scattered by somewhere in the atoms, somewhere in the depth, their energy will be low. So if you find out the energy distribution of the scattered ions, you'll be able to know that the distribution of the dopant atoms also. So that is called Rutherford backscattering spectrometry. So what you see in case of ion implantation and the channeling condition, your distribution of the ions changes. You see non-aligned implantations, so it's not channel, so you have much sharper distribution. But in case of aligned channel, so your RP, it's actually has a tail like this, so you have different RP. Okay, and if a distribution, so width, so that's different. Now as I already explained you that Rutherford backscattering spectrometry, which is also a techniques to use to study the material. Now I was talking about that the Ne, which is use, in this case you use basically the helium ions, and then you detect the energy of the backscatter helium ions. Now if so, those ions which are getting scattered from the surface, their energy will be higher, so you get the higher peak somewhere here which is coming from the surface. Now if something is inside, then of course you will have different place. Now let's say I have two different material mix. One is atoms with mass Ma and another atoms with mass Mb. So let's say my Mb mass are sitting at the um, surface, so you get a higher, the energy loss will be somewhere here, because it's purely from the surface, and you get a peak around this. So that's represent the mass atoms here, Mb, because energy of the backscatter ions by these atoms which is sitting at the surface, they will appear at the higher, so in a higher energy position. But if the atoms which are at depth, so you lose a lot more energy to there to reach there. So these ions will reach some energy there, and the backscatter ion energy also will be lower. So in this case, so therefore we'll be able to identify, just by looking at the backscatter energy, we're able to identify what kind of elements are there and which depth they are sitting. So that's how actually you can understand. And in this case, you have differential cross sections for backscattering ions, which depends on the two atomic numbers of the two atoms that you have. Now this is another example showing that what kind of characterization that you can do using other backscattering spectrometry. You see there are two different cases. In one case you have a film of mass Mb, and in another case it is basically a mixture of two atoms, Ma and Mb. Now in both the cases, if you do the Rutherford backscattering spectrometry, then what you see is when you have the pure B, so you have a like sharp peak at this energy, right, coming from the B atoms, which is a thin film, right, sitting on the substrate. And then of course your backscatter ions profile for the atoms A, which are essentially the for at depth, will be sort of something like this. so you lose a lot of energy here. But in case of mixture, so then you know that this Ma atom and Mb atom both are available at all the energy at all depth. So therefore this will be a little bit broader, because at this point the energy the particle which are coming from the surface atoms from B, and at this edge essentially coming from the backscatter atoms of these atoms at the interface, right? And therefore so this is extended, and similarly here also, you know, you sort of this energy also will be shifted which are coming from atom A. So you see the take home message is, just by looking at the backscatter energy spectrum of the helium ions is completely different, and you'll be able to just model it to see what kind of distribution of the atoms that you have in the atoms. So these are the two extreme cases that I showed, but any kind of distribution which will be reflecting to your backscatter data, and it can be simulated and modeled it and to find out what kind of distribution that you have. So this one is called the Rutherford backscattering spectrometry under channeling condition. Now what you do is you know, you look at the backscatter energy of the backscatter ions, helium ions, and at two different conditions. One is in the random condition, other is at the aligned condition. Now what you see is that if you have a random, so let's say my ions are actually coming in a particular angle hitting the surface, there is no channeling in this case, so you have like higher, you know, backscatter yield. So you have a really high backscatter yield for a random you know, condition when you do the random condition when you bombard the ions. Now if you channel it, so you are aligning the ion beams with the crystallographic direction, then majority of the ions actually passes through, and your backscatter yield is actually reduced. So your forward scattering is more, backscattering yield is more less. So that also can be used to understand you know, a lot more information about the crystal, whether really they're aligned or not. Let's say I have some dopant sitting here and there, and then, you know, you'll get another signal under you know, purely under channel condition, and that is basically used to study the dopant. Now we think that, let's say my dopant atom is sitting here, so you have a higher backscattering rate, but if my dopant atom is sitting in the lattice position, then the backscatter rate is in, you know, low. So we'll be able to estimate using this ion scattering technique as well. Excuse me. Now next, I'll give you one or two examples that where we use the ion beam for different purposes as well. So this is called silicon on insulator technology. So this is normally used, this is called SOI ion cut technology. What you use is, let's say I have a silicon substrate where I'm going to use for device fabrication. So all you need is, you need a silicon dioxide layer at grown at a particular depth, and then again silicon. So this is silicon, this is SiO2, this is again silicon. So essentially, you know, so this layer is silicon, right, and this layer is essentially your SiO2. This is and this is again silicon. Now if I have a wafer like this, then I know I have this is the gate, this is gate dielectric, and this is silicon. Now a selective part of it can be doped as N type, and a selective part can be as P type. So this it will be easier to fabricate a particular device. So how do you make like a silicon dioxide layer in a particular depth? So in ion beam bombardment use. So this one is what is done is that you take two different silicon substrate, right, and in one part you make the silicon dioxide. So just by thermal annealing, you can in under oxygen environment, you can convert this some part of this vapor into silicon dioxide. There are other techniques as well, and then you bond it. So these two pieces are glued together, and then all you have to do is you have to cut the silicon, the first part of the silicon, and at this dotted line. And how to do it? So using the basically in the ion bombardment. So this is like this mechanically. So what you do is you use hydrogen ions, so very light, right? So when you use hydrogen ion, so when you bombard this part, then all the hydrogen ions, because you remember hydrogen is the lightest ions that you have, so at a higher dose, so hydrogen ion will be sitting at a particular depth, so it will be damaging this part of the crystal, and then when you glue it, then it will be easier to break along this line. So that is how actually you can break it, just thermal or mechanical cleavage, and you will be able to make SOI wafer. Now there is another process which is called separation by implantation of oxygen, uh, SIMOX, an alternative SOI technology. So what you do here is that in this case you implant oxygen, and then you implant oxygen. So this is the distribution of the oxygen ions inside the material, and then you anneal it. Then some part, because the silicon and oxygens are there, so they get oxidized, and you make a silicon dioxide layer at the depth. So this is also another technique. So these are all about ion implantation and what one can do with this technique. Now you imagine that the same ion implantation technique can be used to fabricate a device. For example, you take a substrate, some part can be converted into p-type, some part can be converted into n-type, and the distribution. So this is the basically energy band diagram of p-n diode, which you already know. The distribution of the dopant atoms also selectively can be studied. The interface, there will be a lot of diffusion, so you'll have interface distribution will be different. So everything can be studied, and you can fabricate a p-n diode just by converting a part of the substrate, silicon intrinsic semiconductor substrate, into p-type, and another part to n-type material. So with that I stop, and I hope you understand the ion implantation technique, and of course ion scattering technique also can be used for characterization of material. One of the important technique is called ion Rutherford backscattering spectroscopy, which also is very standard techniques and very powerful technique to study material surface and interface. So thank you.